10. Well, now it is 10. So we'll get started here. Let me share my PowerPoint. Minimize that. Hide that. All right. So what we were talking about on Monday was this idea of energy, right? And so just as a quick refresher here, we talked about the 4 different types of energy: kinetic, thermal, potential, and chemical, which is actually a type of potential energy. Did some basic energy calculations. Well, just units for energy, I should say. Then we looked at internal energy, which is a state function. We talked about this delta symbol, where delta, every time we see delta in chemistry, that means change, right? And it's always going to be final state minus initial state. And for a reaction, if we want to measure the change of energy of a reaction, that is products minus reactants. And we did, then we talked about how energy can't be created or destroyed. So any energy gain from the system must have come from the surroundings. And if the system loses energy, that has to go into the surroundings as well. And we talked about endothermic and exothermic. So if we're talking about heat or energy or anything that uses endo or exo, the way to remember which one's which, endo means in, so it's going into the system. Exo you can think as exit, so it's exiting the system, right? So if it's endo, it's going in, exo, it's going out. So that's where we ended on Monday, right? Now let's talk about how systems in the surroundings actually exchange energy. And the way that energy is exchanged is through either heat or work. And we call that Q and W. So another thing to note in chemistry, you're going to see Q when you go on the Gen Chem 2 as well. Every time you see Q, that means like heat or temperature. So we use Q for heat. So when we calculate the change in energy, we can break that down into actually more parts where we're calculating the difference of heat and the difference of work. So if my system gains heat, Q is positive. If it loses heat, Q is negative. If the surroundings do work on the system, work is positive. If the system does work, W is negative. So you can think of work as like a spring, right? If I take a spring and push it down, I'm doing work on the spring. If I release the spring and then it uncoils, the spring did work. So me pushing down on the spring, work would be positive for the spring. When I let go, work is now negative because it's expanding, it's doing work. So on Monday, we talked about energy being a state function. What a state function is path independent. Remember, I talked about the mountain. If I climb the mountain or if I take a helicopter up to the mountain, it doesn't matter because my change in energy are the same. However, heat and work are path dependent, right? Me climbing up the mountain would be work compared to me flying up the mountain, which really wouldn't be work. So Q and W are not state functions. Energy is a state function. So any questions about that terminology. Now we'll jump right into some math surrounding this. All right, so our first question, I believe I actually have a poll for this one, is we're just gonna look at some scenarios and determine if we're doing heat, if we're exchanging energy via heat, or if we're exchanging energy via work, and then determine if delta E is positive or negative. So let me pull up the polls here. That would be question 3. All right, so I just have whether it's heat or work. Then I want you to write down, once you have that, whether the change in E for the system is positive or negative. So the poll has the actual questions. I want you to answer if I'm doing heat, or if I'm transferring energy via heat, or if I'm transferring energy via work. And then once you figure that out, I want you to think about, okay, based on what I said, is delta E negative or delta E positive? So that's where we'll begin here. Do about another 40, 45 seconds. All right, I will end the poll and I'll share the results. So it's a good thing that I asked this poll, because it looks like there's some confusion and how to define transfer via heat or transfer via work. And so this is actually an easy thing to look for in these types of problems. So if you're doing transfer via heat, you'll have a temperature change. If you're doing via work, you won't, it's not going to mention like a temperature change, right? So if I have a billiard ball, right, and I hit another billiard ball that goes off flying, that's all work. I'm doing transferring energy via work. I'm not transferring energy by changing the temperatures of the billiard balls. I'm transferring energy via work. And delta E for the first one, if our first billiard ball is the system, delta E is negative, because when I hit the second billiard ball, I'm transferring my kinetic energy to the second billiard ball. Therefore, if I'm the first billiard ball, I lost all that energy. I stopped moving. So I lost that kinetic energy. I lost it in the form of work. Note, I will say that in these processes, there is some transfer of heat due to friction, but it is so small compared to work. We're not really gonna worry about it. That's why it's like, what is the main transfer of energy? Yeah, the friction is just so low compared to like work. It's basically not a variable. Okay, book falls to the floor, same thing, work, right? I'm not changing the temperature. If I'm the book, I'm not changing temperature when I go through the floor. So that is work. And it is negative, delta E is negative. I'm losing potential energy. I mean, technically, that potential energy is being converted to kinetic energy via movement in gravity. And then when you hit the ground, you will release your energy as heat. But while I'm moving to the floor, that is all work. Again, the easiest way to determine what type of energy exchange is going on is, are we changing the temperatures? When I'm moving to the floor, I'm not really changing the temperature all that much. At the very last step, yes, I will lose my energy in the form of heat, but mainly what's going on is that gravity is doing work on me. Okay, a father pushes his daughter on the swing. The daughter and the swing are the system. So that's work. So it looks like we pretty much got that. Delta E is positive, because if you're the daughter in the swing and you're getting pushed, you're getting energy put into you. You're having more kinetic energy. So that is all work. It's not like the dad has like a blowtorch and it's like putting heat into you and that's why you're moving. You would move because of that, but that is not what's going on here. Any questions about heat versus work, or if delta, how we can tell if delta E is positive or negative or anything like that? All right, if not, we'll move on. Yeah. Question 4, time for some math. A system absorbs 196 kilojoules of heat. So instead of or heat, that's supposed to say of heat. And the surroundings do 117 kilojoules of work on the system. Or this might change in internal energy. So I'll give people like a minute for this one. I always find it nice to draw pictures of system, surroundings, and the arrows of Q and W will tell me which directions I'm going in this. Oh, by the way, any of you who like to play Lotteria, there is a Lotteria happening via the Chemistry Club at 1 p.m. To join. Just go to JagSync. No cash prizes will be given. I think there will be prizes though, because there were last year, just not cash. But like last year, I won Waterburger coupons, so I mean, that's always good. All right, so first thing I want to do is draw my arrows. So Q, heat, is going from the surroundings into the system. Work, so the surroundings is doing work on the system. So both things are flowing into the system. If they're flowing in, they're positive. So both of these values are positive. So my change in energy is Q plus W, which is 196 plus 117 equals 313 kilojoules. So the hardest part of this is just figuring out, is QW positive or negative? So that's why I like to draw the image there. If it goes into the system, positive. If it leaves, negative. Questions about that idea? Again, fairly simple. Or fairly simple equation, I should say. What makes it negative? If it flows out of the system, right? If I said a system loses 196K, so if I'm losing heat or if I'm doing work on the surroundings, that's when those values become negative. So I'm losing energy. It's positive if I gain heat or if something's doing work on me. Again, the way I remember that is the spring. If I'm being compressed and I'm the spring, I'm building up that energy. So I'm getting work on me. So energy is positive. If I'm the spring and I'm no longer being compressed and I release, well, now I'm doing work because all that energy that was built up allows me to expand now. So releasing the spring loses energy. All right. Last question for this PowerPoint. So I have a balloon, and the balloon's my system. I put that balloon over the toaster. I did it again. Absorbs 115 joules of heat. When it is expanding, it is doing 77 kilojoules of work. What's the change in the energy of the system? Again, I'll give people like a minute or two to figure that one out. Same equation, delta E equals Q plus W. Your main task is to figure out, is Q positive or negative? Is W positive or negative? The way to really do that, at least for me, is to draw a picture to figure out what's going on. It is not positive 38. Might want to check your units. Your units. Your units. What are our units? I cannot add a joules to a kilojoules. Not 115. What are my units? People forgot what a kilojoule means. Haven't been learning your metric system. I told you the metric system would always be there. So kilojoules, right? It's 1,000 joules. So this is 77,000 joules. So if I have a balloon, right, and it's doing work, so work's negative. If it's getting heat put into it, heat's positive. So delta E equals 115 minus 77,000, right, joules. You could also put the 115 in kilojoules if you wanted to. That's why it's always important to tell me when you answer stuff what unit is it in, because I don't care if it's in joules or kilojoules, because joules and kilojoules are the same thing again. So that is negative 76,885 joules. Any questions? And don't forget your units. Units mean a lot. Units are very important. There's a big difference between having a million pennies and a million $100 bills. All right, so that's it for this PowerPoint. Let's move on to the next PowerPoint. No, I don't want my ink annotations. Yeah, 1021, where we're going to continue to talk about energy. And our calculations are going to get a little more complex, as they always do. All right. What we're talking about here is heat capacity. Heat capacity is basically how much energy it takes to heat up a substance. The actual definition is like, let me get my pen out, is how much energy it takes to heat up a gram of a material 1 degree Celsius. So joules is energy, G is grams, C is Celsius. And it really depends on the substance. Like water has a very high heat capacity. It takes a lot of energy to raise the temperature of water, right? A lot of energy. While something like asphalt takes very low energy, right? It has a very low heat capacity. If asphalt is just, in the good old Texas summer for like 8 hours and you try to walk on it barefoot, you are going to burn your feet. But if it's just a puddle of water or grass, you can walk on that barefoot, no problem. You're not going to burn yourself, right? So water and grass have high heat capacity. Asphalt has low. So the higher the heat capacity, the harder it is to raise the temperature. Hard to raise temp. The lower the heat capacity, the easier it is to raise the temperature. And there's been calculations done that have measured what's called the specific heat capacity. This was the unit I was talking about. And it looks like it got a little bit wrong. Is joules divided by gram Celsius. The amount of heat to raise the temperature of 1 gram of substance of 1 degree centigrade is called specific heat capacity. And we also have molar heat capacity. The amount of heat required to raise the temperature of 1 mole of substance by 1 degree centigrade. And these are intrinsic properties. That means it doesn't matter how much stuff you have. The specific heat capacity never changes. Like you can have an ocean of water versus a glass of water, and the value of specific heat capacity doesn't change. Here, I just have a table of different specific heat capacities. You don't need to memorize these. We're going to use water a lot. And as you can see, water compared to like a ton of other materials, the specific heat capacity of water is just massive. That's why it takes so much energy to boil it. That's also why it takes so much energy to freeze it, right? To freeze like a body of water takes weeks below 0 temperature before it freezes over. It just really doesn't freeze that well overnight. It takes a long time to do that. So how can we measure this heat energy with specific heat capacity, right? What I'm really asking here is, if I give a substance so many joules of heat energy, what is its change in temperature? That's what this equation is saying. If I supply a certain amount of heat, what is the change of temperature? That depends on the mass of the substance and the specific heat capacity of the substance. Why does liquor not freeze? Liquor does freeze. It just takes colder temperatures. The thing is, and when you take Gen Chem 2, this is like one of the first topics you actually talk about, is called a colligative property, right? And a colligative property is the more stuff you have dissolved in water, this is just an example. The more stuff you have dissolved in water, the lower the freezing point goes. So liquor is usually 35% ethanol, right? So 70 proof liquor is 35% ethanol. And so the freezing point of liquor might be like minus 10 degrees centigrade. I actually don't know off the top of my head. And water is 0. So it will freeze. You just need to be much colder than like normal freezing point. But yeah, it's just because it has this stuff dissolved in it. Is everything with a harder heat capacity harder to freeze? It takes more energy to freeze, but the actual temperature at which it freezes at depends on the material. Yeah, so if we go to the other table, ethanol had a heat capacity of like 2 or something. So yeah, it takes less energy to freeze ethanol than it does water, which has a heat capacity of 4.184. So yeah, it's really, the way to think about this is the higher the heat capacity, the more heat you have to put it, the more energy you have to put in to heat something out, or the more energy you have to take away to freeze it. So in a word, yes, it is harder to freeze. All right. So the equation we're using is Q equals mcs delta T. The amount of energy I put in is equal to the mass times the heat capacity times the change in temperature. Again, when you see delta, final minus initial. So let's do a question to get used to this equation. I have 250 milliliters of water. This water is at 37 degrees C. This water loses 342 joules of energy. What's the change in temperature if the density of water is 1.00 grams per mil? And I give you our specific heat capacity table. So I'll give everybody a few minutes to try and figure out this question. Okay. So the freezing point of 70 proof alcohol, I just Googled it, is 5F and water is 32F. So yeah, it will freeze, or minus 15C and water is 0C. Not going to freeze in Texas, but if you leave liquor in your trunk during an Iowa winter, that thing will freeze and it will burst. It will shatter that container. And you might be asking yourself, why doesn't it freeze when you put it in your freezer? Your freezer is not that cold. That's why. All the stuff we can learn with chemistry. Then if you take biochemistry, we can talk about why ethanol makes you drunk and methanol will kill you. But that's about at least 2 years away for some of you. Gotta go through organic first. If you thought general chemistry is hard, just wait for organic. All right, so I'm sure people are still working on this, or I hope you are. So the first thing we want to do is just decide what our variables are. And like I said, I always draw pictures for word problems. It makes it so much easier for me. So we have water, red water, I guess. And it's going to lose 342 joules of energy. So Q is negative 342 joules. So we have a Q. Mass. We have a density and we have a volume. So density is our conversion between volume and mass. So I have 250 milliliters. For every 1 milliliter, I have 1 gram of substance. So for water, it's super easy. 250 milliliters is 250 grams. I'm going to warn you right now, I might not give you water on the test. So do not just assume the volume is the same thing as the weight. That happens every year when I give something different than water. Just know to convert between a volume and a weight, you need density. For water, the density just happens to be 1 gram per 1 mil. All right, so we have a heat, we have a mass, heat capacity is given. Delta T, T is final, delta T is T final minus T initial. So initially, I'm at 37C. Finally, I don't know. I'm trying to solve for that. So 1 equation, 1 unknown. So before I go to solve this problem, is there any questions from anybody how I decided on my variables or how I more or less set this up? Because just deciding your variables is the hard part. Plugging it in should be the easy part. So let me know if you have questions about what I did there. Where did you find CS? CS is given on the table. Given on the table. Like I said, I won't expect you to memorize CS. So I'll either have to tell you CS or the problem would be solved for CS. Remember, CS means specific heat capacity. That's what CS is. All right. You are solving for final temperature. That is correct. Let's solve then. So minus 342 equals 250. So let me joules, grams, multiplied by 4.18 joules, grams, centigrade, multiplied by T final, don't know, minus T initial, 37. So the way I would do this is I would get this parenthesis by itself. So it is minus 342 divided by 250 times 4.18 equals T final minus 37. Solve for that. You should get negative 0.32696 equals T final minus 37. Add 37 to each side. T final is 36.7. So, and you should check yourself. Does my answer make sense? I lost heat, so I lose heat, so my temperature should go down. It does. It went from 37 to 36. It looks like that, but 36.7. So I lost some temperature there. I did not get 33. I got 36.7. Let me just double check. While I double check, questions about that? 342 250 times 4.184. Yeah, it should be like 36.7 roughly. The units are centigrade. I'm solving for a temperature. No, the answer would be 36.7 because you solve for temperature final, right? Because delta F, or sorry, delta T, right, is final minus initial. Temperature final minus temperature initial. We're solving for temperature final, so that's the answer. Uh, 37 minus 36.7 is that is delta T, but we want T final. Okay. All right. So any other questions about that, or we'll move on to our next related idea. All right, moving on. We can use this idea of specific heat capacity in calculating transfer of thermal energy between two different substances. So let's say I have a slab of metal, as shown here, and it's hot, and I put it in water. And let's say this is perfectly insulated. That is, I don't lose any energy to the outside environment. Well, since this is an isolated system, any temperature change or any heat gained or lost by my metal had to come from the water. So let's say in this example, my metal was actually colder than the water. Sure. So let's say my metal gained 100 joules of energy, thermal energy. Based on my system, the only way or the only place that energy comes from is the water because it's isolated. It can't get it from the surroundings. So if my metal gained energy, the water must have lost that same amount of energy. That's why we have a negative sign here. So the thermal energy gained by my metal is equal to the thermal energy lost by the water. And it's the same idea here. So if my metal lost 250 joules of energy, thermal energy, then my water must have gained that. All right. So although the negative sign is in front of the water, that does not mean the water is always negative. All that means is that the metal and the water have to have opposite signs. So for thermal energy transfer, the Q's have the same number, but opposite signs. One has to be positive and one has to be negative. Always, always, always. Unless it's 0, I guess. Can I send you a message on how you chose the variables? Yeah, let me do that in a little bit. So when we're doing this problem, right, we're doing Q's again, and we just looked at how to measure Q's. So Q metal is simply mass of metal, heat capacity of metal, delta temperature of metal. Q water is mass of water, CS of water, delta temperature of water. Again, delta is final minus initial. All right. Any questions about the information on that slide? All right. If there's not, let's try it out. I have silver, heat capacity given. It's at 58.5 degrees centigrade. I put that into 100 grams of water at 24.8 that has a CS of 4.18. It's insulated, so we don't lose any energy to the surroundings. It's only the block in the water. That's what insulated means. We only care about the block in the water. The final temperature of the silver in the water is 26.2. Therefore, what is the mass of the silver block? See if we cannot solve this problem. So question here is the final temp of 26.2 delta T of water. That is not delta T, that's just temperature final. That's just T final. You have to solve for delta T, and I give you two different T initials. All right, let's just start with declaring our variables as always, right? So if we just read the question, what is the mass? We don't know that. And let me draw my picture here. So we have a silver block. No, I don't have silver, so it's going to be black. And that's in water. There's our picture. Okay. The mass of metal, I do not know. CS of our silver, I do know. 0.235. Delta T, well, T's final minus initial. So at equilibrium, when everything's the same temperature, is 26.2. So that's my final. While initially it was at 58.5. That is equal to negative. Remember, one of these Q's have to be negative. It doesn't matter which Q you call negative at all, because it will work out. But one of these have to be negative. So let's just go with the equation and say the Q of water is negative. So it's submerged in 100 grams multiplied by the CS of water multiplied by the temperature of delta T of water, final minus initial. So at thermal equilibrium, it's 26.2, while initially it was at 24.8. All right, any questions about how I got my variables? I'm just going to call that M, I guess. Because once you have the variables, it's just algebra at that point. If you got all the variables right, but the wrong answer, you might want to check your calculator. Sometimes when you plug it all in, it does not do what you think it's doing. All right, so I'm going to solve for M. So M on one side, divide each side by this parentheses. So it is negative 100 multiplied by 4.184 or 4.18. So I'm adding that extra 4 because that's one of the numbers I've had memorized, and I know how it goes out to another 4, but 4.18 is fine. Multiplied by delta T, 26.2 minus 24.8, divided by 0.235 times 26.2 minus 58.5. All right, so here's a word of warning for people. If you put this into the calculator exactly how I wrote it, it will give you the wrong answer because it'll do everything at the top correctly, and then it will divide by 0.235 and then multiply the whole answer by this delta T. So be careful. That will happen if you just throw it all in the calculator at once. How did you get the variables? M is unknown. CS is given in the problem for the metal. Delta T, the initials given, finals given for the metal. So that's why I chose 20, that's water, my bad. Final is given as thermal equilibria, so 26.2 is my final. Initially, I was 58.5. Mass of water is given. CS of water is given. Delta T, final was given 26.2. Initial is given 24.8. So can we use the final temp to find delta T of both initial temps given? So I think I understand what you asked, but it was kind of worded weird. I think what you're asking is, do we use the initial and the final and the same final for both? And yes. So thermal equilibrium means that the temperatures are the same. So if I have a metal block in water and they're at different temperatures initially, and I put it in there, they will be the same. All right. And when I do this, I get 88.8 grams. As always, let me double check myself. Before I get yelled at that I gave you all the wrong answer. And it's all my fault. And I get yelled at some more because I gave you the wrong answer. That's why you learned it wrong. So it's all my fault, as always. So let's see. H4 divided by 0.235. 6.2 minus 58. Yep, 88.8. All right. Any questions on solving this type of equation where we have specific heat capacity, but we're doing thermal exchange using our specific heat capacity and our equation for calculating thermal energy? I know, I'm just kidding. I'm playing the poor sap just because we had a 15-minute debate in biochemistry on Monday about how, because I drew something different than what I showed on the test, it's my fault for learning it wrong. Anyways, that's not a discussion for Gen Chem. All right. Well, if there are no questions, so let me just say, for those of you who are watching the video or have stuck around, like this is a question I like always ask on the test, and like 80% of people get it wrong. So make sure you know how to solve this, right? It's just using the Q equation twice. Make sure you know how to do something like this. And just to be forewarned, I might not always ask you the mass. I might just ask you like, okay, what's the CS of the metal or something like that. But yeah, expect to see this type of question in your future. All right. If there's no other questions, that's all I have for you. It is time for us to depart. Yeah, I'll put a homework up as always. And if you have any questions, feel free to always email me. Otherwise, I will see everybody later.